Hello, I'm Rachel, and my topic is Ceph on Arm64. Uh, it's about our practice of Ceph storage ecosystem on Arm servers. This is the agenda of my slides. Firstly, I will give an overview of the Ceph-related work we have done on Arm servers. Yeah, this is the framework of Ceph. Our practice to enable and improve Ceph storage ecosystem on Arm64 includes using Arm-specific instructions or features to do some common Libs optimization, like UTF-8, CRC, SAL. And some of Ceph's features requires the support of some sub-projects. So we also enabled those server projects on Arm64, including SPDK, Seastar, Ceph CSI, and so on. Besides, we also try to do some optimization in these server projects. And the support to use Ceph as storage Ceph backend for OpenStack Kubernetes on Arm64 has also already been done. Yeah, we keep trying to leverage Arm CPU features to optimize Ceph common labs. Yeah, it's not easy as most Ceph codes are already highly optimized, but we still try to find some potential points to optimize, especially for Arm architecture. The following is some optimization we did in early days. One is the optimization of UTF-8 string handling. UTF-8 is a variable length coding method for Unicode. The original implementation, encoding and checking is done per byte. It's not so efficient. Our optimization can give up to 8 times boost for string validation and 50% gain for string encoding through operating several bytes at a time. And another optimization is about the widely used CRC32 implementation. With Arm v8 PMAL instruction, we can achieve up to 3 times performance boost on platforms where CRC extension is available. About Ceph and ISAL library. ISAL is the Intel Storage Acceleration Library. It provides algorithms to help accelerate and optimize our storage. The functions provided in this library help with data protection, data integrity, and data security. In Ceph, ISAL can offload support for compression, encryption, and so on. And in this library, we have added support of CRC IGZip, RAID, AES, GCM for encryption, and different multi-buffer algorithm implementations like multi-buffer MD5, multi-buffer SHA-1, SHA-256, and so on, and multi-hash SHA-1, SHA-256, and loading hash using specific features in instructions. Besides, because ISAL provides multi-binary versions of some functions, developers can deploy a single binary with multiple function versions and then choose features at runtime. For Arm64, we added the utility functions to get the CPU feature set and provided a framework to get the right function based on the feature sets. And now we are working on some other algorithms like AES, STS, and multi-hash SHA-1 plus murmur-3. If you are interested in the implementations, you can refer to ISAL and ISAL Crypto GitHub for details. The related code is put under Arm64 directory. We also enabled and benchmarked Ceph on 64 KB kernel page. Because ARM has 64 KB kernel page support, a large page has some benefits compared with a small page. On ARM platforms compared with 4K, a 60K page system removes one level of page table, which brings faster TLB lookup. Besides, it can improve TLB hit rate, for each entry can traces a larger memory region. Now there are already some pages to support Ceph under 64 KB kernel page and to solve some memory waste problem. Here we used a Ceph test cluster with one monitor, one manager, and 3 OSD to do the benchmark. Each OSD's backend is one P4016 NVMe SSD. We tested the RBD sequential and random read and write with different block size. This is a performance with only 4 CPU cores activated on the cluster side. The yellow bars are the Ceph RBD bandwidth of 4 KB kernel page size, and the orange ones are 64 KB kernel page size. From the graphs we can see we can get about 3 to 11% boost for read, according to different block size from 4K to 4 million byte block size. And for write is 8 to 22% boost, set to 10% for random read, and about set to 15% boost for random write. So in this test case, using 64 KB kernel page size, does bring some benefits. This is also the RBD performance. It's with only 2 CPU cores activated on the cluster side. The performance difference for write and random write, it's more obvious. At 4 KB block size, it's about 12% performance gain, and for 4 million byte block size, it reaches about 33%. In addition to the work we have done, we are investigating new optimization points, like leveraging new feature, a scalable vector extension called SVE for short to do some optimization. Also, we can try to leverage the non-temporal instructions to prevent cache pollution in some cases. And we are also investigating the LogsDB compression labs optimization potentials. And then we go to self-storage with SPDK. SPDK, the storage performance development kit. It can achieve high performance by through moving all of unnecessary drivers into user space and operating in a pod mode instead of relying on interrupts, which can avoid kernel context switches and eliminate interrupt handling overhead. In Ceph, SPDK can be used to accelerate the block service built on Ceph. We can use SPDK's user space NVMe driver instead of kernel NVMe driver in BlueStar. And besides, as mentioned in this link, SPDK iSCSI target or NVMe fabric target can be leveraged to accelerate client I/O performance on Ceph cluster by introducing some caching solution. We have also done a lot of work in SPDK, including enablement and optimization on Arm64. It covers the optimization of some common algorithms like base64, which is used to encode binary data to printable ASIC2 characters and decode such encodings to binary data. With Arm intrinsics, we can achieve up to 2.3 times boost for encoding and 1.7 times speed up for decoding. Besides, we did some optimization related to the memory barrier. We know that most modern CPUs employ performance optimizations that can result in out-of-order execution. This reordering of memory operations can cause unpredictable behavior in concurrent programs, especially when we write multi-thread and block-free code. So we need memory barrier to enforce an ordering constraint on memory operations issued before and after the barrier. Unlike x86 strong memory model, ARM has a weak memory model, and this essentially means that few guarantees are given as to the observed order of CPU memory access. Thus, any load or store operation can effectively be reordered with any other load or store operation, as long as it will never modify the behavior of a single isolated thread. Rationale behind a weak memory model is that it places fewer constraints on partners and provides a lot of scope for hardware optimization. In practice, we can use more precise constraints to make fewer instructions outside our code sequence affected by the barriers. For example, we have DSB, DMB, and ISB. The DSB is the date synchronization barrier. It completes when all instructions before this instruction completes. And the DMB is the date memory barrier. Ensures that all explicit memory accesses before this instruction complete before any memory accesses after the DMB instruction. So we can choose the one according to the detailed code context. For instance, if we just want to ensure the memory access is in order, DMB is enough. And there is also a half barrier, load acquire and store release, which can be used to further relax the barrier. And besides, we can replace the sync built-ins like sync, fetch, and add with the atomic built-ins, or just use atomic functions provided in V11 to remove some unnecessary full barrier. Actually, they are used in the SPDK and widely used in DPDK. Now, DPDK has adopted the C11 memory model to develop a robust code that performs best on all supported architectures. Apart from the above, we also did some optimization in SPDK NVMe of TCP. For example, we can leverage TCP's incoming CPU feature to get the CPU affinity of a socket. And then we can distribute the processing of this socket to specific CPUs, which provides optimal normal behavior and keeps the CPU cache hot. And this can bring about 10% performance boost in our test. And all the related pages are ready in SPDK projects. There are some other optimization in SPDK, but I'll not go further on this. Let's go back to Ceph. Go back to Ceph and SPDK. And this is the performance state of Ceph with SPDK on ARM servers. The test cluster contains 3 OSD and 1 P4610 NVMe per OSD. we collected the 4 KB sequential and random read and write dates. The yellow bar is based on BlueStore without SPDK, and the orange one is with SPDK. From this graph, we don't see any obvious performance improvement in our test case. And there is even some drop in write performance here. It seems it's hard to get benefit from SPDK with the traditional Ceph OSD framework. More work needs to be done. Now the Ceph OSD is being refactored based on Seastar's high performance framework for the age of persistent memory and faster NVMe storage. Seastar, it's a shard-nothing design, and each core has its own resources. And it uses message queue for communication between cores, and I think all this makes it a natural fit for ARM architecture with many cores. About Seastar, the work we have done includes upgrading Seastar DPDK to leverage new hardware. Because Seastar has DPDK and path to achieve the zero copy between Seastar heap and NIC. It uses a physical address for DMA by referencing the file proc self page map, which is a legacy method, and this update leverages IOMMU to map Seastar heap virtual address directly to IO virtual address for DMA purpose, which makes full use of modern hardware and significantly simplifies the code. And this upgrade also upgrades to new offload API. Besides to make Seastar work on Arm64, we also fixed some bugs like network stack crash issue on ARM and fixed Seastar 64 GB per shard memory limit. For the network stack crash issue, actually it's caused by a code snippet like this. It's a function call with 2 parameters. First parameter is function to free a pointer, while the second as the reference the pointer. This code was okay on x86 as parameters passed from right to left in stack pushing order. So the second parameter use pointer is called before the first one, the free pointer. By fails on ARM, as parameters are passed from left to right to leverage abundant general purpose registers. So free pointer will call before use pointer, which can lead to crash. So we need to save the parameter contents before calling this function. This is the Seastar HTTP benchmark on ARM servers. We can see that the performance scales up almost linearly with the addition of the CPU cores. But actually, we haven't verified and benchmarked Seastar on ARM server. We will do this later, and see how the performance is. And finally, we will go to our work about bringing Ceph to the cloud on Arm64. Currently, Ceph as OpenStack storage backend is mature on Arm. The basic functions like using Ceph as OpenStack Swift, Cinder, Glance backend work well on Arm64. And in addition to OpenStack, we have supported Ceph as Kubernetes container cloud storage backends on Arm64. We added the official support for some critical container images, such as the Kubernetes CSI sidecar image, and added an image support for Ceph CSI community. Also added jobs in its community CI. Yeah, we also support Look on Arm64, which can simplify the deployment of Ceph cluster in Kubernetes. Yeah, and the following related work we plan to do includes supporting container object storage interface on Arm64 and some work about the Kubernetes storage E2E test improvement. Yeah, yeah, I think that's all I want to share here. Any questions?
I have a bit of a long question from Dan in chat.
Okay, thanks. Well, it was interesting. I guess I'm a naive user, but I didn't realize that other architectures can implement the ISA libraries. So my question is basically like, until now, we didn't ever use ISA for erasure coding because we're afraid of being locked into Intel. Like from an operations point of view, can we safely use ISA erasure coding and then be free to move to other CPUs, non-Intel in future with the same OSD pools, same OSDs or same pools?
Hello? Hello, can you hear me? Hello?
Yes.
I'm Igor. Yeah. I work with Richael. So for ICL, I'm more familiar with it. I did some work in the ICL library. So you mean ICL means the ICL, the Intelligent Storage Accelerator Library? Yes. So for ICL, actually, we implement some ARM-related accelerator codes to the ICL library. And for EC, I remember Huawei has upstreamed their implementation of ARM-based EC in the ICL library. So I think this is the ICL library supports both Intel and ARM.
Okay, thanks. We'll test it.
Yeah. Okay.
I would imagine what we really want is a mixed cluster that has some Intel nodes and some EPYC nodes and some ARM nodes in the same pool, and then make sure that everything behaves as expected.
I mean, yeah, thanks, Sage. I mean, it was Andreas at CERN. He wrote the first ISA library for EC. But yeah, like I said, we've never even used it because we had the impression that, I mean, our vendors will switch us to AMD at any time. Actually, our next block is EPYC, and we were just afraid to ever use it.
I guess the other thing you might take a look at, I believe that there's an erasure code non-regression data corpus. That's part of the repository. I'm not sure if it's been like refreshed with new data as new EC libraries have been added, but probably should be. But the idea there is that there's a whole bunch of erasure coded data that's stored in Git, and then the unit tests just like read it and make sure that it's readable. So that might also be a good.
Yeah, I guess. And in the lab, you have mixtures of different CPUs.
We have a new set of machines that are EPYC, but they're not used for unit tests or anything. And we do have a bunch of ARM nodes that do run the unit tests. But I would probably review the unit test and make sure you understand what it's actually testing before drawing any conclusions.
Okay. I guess also it's like it's one thing if it works, if you can read it in, but also it should be performing well. It shouldn't be like emulated or something.
Yeah.
Okay. Thanks.
Cool. I was impressed that Danny mentioned in the chat 8 to 12% improvement over 4K, and there were almost identical results in this deck too, like 9 to 11% or something.
Yes.
Yeah.
You have any more questions for Rachel? Okay. All right. Thank you, Rachel, for the presentation.
Yes, thank you.
Thanks for listening.
Thank you.
So I guess since we have a couple of minutes,
Oh,
I have just out of curiosity here. John in the chat was mentioning a Raspberry Pi 2, Pi 4. I'm curious what people who are running stuff on ARM on Raspberry Pis are using for the actual storage, because maybe the Pi 4 has beta ports, but the 3 I think didn't, right? You had to use like a USB adapter or something like that. Is anybody on using the Raspberry Pi?
Do you mean Raspberry Pi?
Yes. Okay. Yeah.
I actually have a colleague that has a Raspberry Pi cluster at home. He talks about it all the time, way too much. I don't actually know what he's using for the data. I always assumed it was just USBs and that he only just maxed out the data ports that you're talking about. And then if you have like 5 or 6, then that's the limit of like 5 times 3, 15 OSDs, right? But I don't actually know. I can ask him. I think he's on holiday at the moment.
I guess that question could go to Mike actually, because you put together a Raspberry Pi cluster, right?
yeah. It's along the same lines of using a USB adapter though as well.
Yeah. Okay. I was going to set one up just so I can locally the ARM stuff, but we also have a bunch of ARM nodes in the lab, so it's not entirely necessary.